Introduction to Set Theory. A set is an unordered collection of objects, and these objects are called elements or members of the set. A set is said to contain its elements, and we write A is an element of A to denote that A is an element of the set A. So this symbol here denotes that A here is an element of the set A. The notation A is not an element of A denotes that A is not an element of the set A. Here, again, this is read as is not an element. So when we talk about sets, just imagine set as a circle, okay? And this circle contains the elements of the set or objects of the set, since basically it's just a collection of objects, right? So let's say we have here a set of the colors of the rainbow, for example, colors of the rainbow. So this circle here or this set here, let us call this set R for rainbow. So set R would be a collection of objects, and these objects or elements are the colors of the rainbow. So what are the colors of the rainbow that we know of? We have red, we have orange, we have yellow, we also have green, blue, violet, and indigo. Right? So these colors here are the elements of or members of the set. And if we want to say that red is an element of set R, we could write that as red element of R, right? And if we have an object that is not an element of set R, for example, what is a color that is not part of the rainbow? Let's say we have black. Then we write that as black, not an element of R. And that is how you do the notation when we talk about set and its elements. The roster method. Okay, one way to describe a set is to just list down all the members of a set when this is possible. We use a notation where all members of the set are listed between braces. So let's say we have here a set V that represents or would represent the set of all vowels in the English alphabet. And using the roster method where we list down all the members of the set, that is basically that's basically written as V. The set V is equal to the set where the elements are A, E, I, O, and U. The braces here would represent the set. Okay, the members of the set are listed between braces, and that is how roster method works. Example number 2, we have here the set O of odd positive integers less than 10. And what are the elements of that set? The elements of that set are 1, 3, 5, 7, and 9, and these are found in between braces because again these tells us that 1, 3, 5, 7, 9 are members of the set O, which is the set of odd positive integers less than 10. And that is how rostered method is done. Although sets are usually used to group together elements with common properties, there is nothing that prevents a set from having these seemingly unrelated elements. Sometimes the roster method is used to describe a set without listing all of its members. Some members of the set are listed, and then ellipses, 3 dots, are used when the general pattern of the elements is obvious. So for these 2 paragraphs here, we have these examples 4 and 5. For the first paragraph, it says that the elements in a set does not really have to have relationship to each other. For example, we have set U here where the elements are A2, Victor, and Detroit. These elements or these members of the set do not have a relationship at first glance, right? Still, it can be a set. Okay, you could have unrelated elements for a set. Example number 5 would be an example for the second paragraph. If we know the general pattern of the elements inside the set, we could not list down all the elements of the set, and we could just use ellipses to represent this. The set of positive integers less than 100 can be denoted by 1, 2, 3, ... 99. Okay, because there is a general pattern where it increases 1 unit, so we know that in between these ellipses would be the numbers 4 to 98 until 99. Okay, now aside from roster method, we also have set builder notation. So another way to describe a set is to characterize all those elements in the set by stating the property or properties they must have to be members of the set. Now the set O of all positive integers less than 10 can be written as O is equal to the set of X such that X is an odd positive integer less than 10, or O is the set X that is an element of the set of positive integers such that X is odd and X is less than 10. So the bar here represents such that, and again this here is read as is an element of Z positive here means set of all positive integers. So basically O is the set of all elements X that is an element of the set of all positive integers such that, okay, this is such that X is odd and X is less than 10. So this is the property or properties, right? Because we have two properties that they must have for X to have to be a member of that set. Okay, here are some of the general sets that we usually use in set builder notation. N would represent the set of natural numbers. Those are the counting numbers with 0. Z here would represent the set of integers. Now, if Z has a positive sign, then that's the set of positive integers. Likewise, if we have here Z negative, that is the set of negative integers. Okay, Q is the set of rational numbers, where P and Q, small p and q, are elements of the set of integers. R is the set of real numbers. R positive is the set of positive real numbers. And again, same with the Z negative. If here we have R raised to negative, then that's just the set of negative real numbers. Okay. For set builder notation, we also have to recall that the notation for intervals of real numbers differ when we use braces or parentheses. When A and B are real numbers with A less than B, we write this. Now remember that if we have brackets, okay, these are brackets, then this is called the closed interval from A to B. And when we have parentheses, then this is called the open interval from A to B. Therefore, here we would not include A and B if it's an open interval, and if it's a closed interval, then we would include A and B, because here you could see that X such that A is less than and equal to X, and X is less than and equal to B. So X is equal to A and B when it's a closed interval, but X is not equal to A and B when it's an open interval. We also say sets are equal if and only if they have the same elements. Therefore, if A and B are sets, then A and B are equal if and only if for all values of x. Okay, here this is read as for all. So for all x is an element of A if and only if. Okay, this double-headed arrow is read if and only if x is an element of B. And we write A is equal to B if A and B are equal sets. Example number 6. The sets 1, 3, 5 and 1, 3, 5, 1 are equal because they have the same elements, which are 1, 3, and 5. The set 1, 3, 3, 3, 5, 5, 5, 5 is also the same set as the other two because they also have the same elements. The repetition of the element would not matter in the equality of the set. So even if 3 gets repeated here and the first two sets only have 1, 3, it's still equal in terms of its elements. That's why we still say that these sets, the first, second, and the third one, are equal to each other because they have the same element. A set is said to be an empty set, and this is a special set that has no element. So it is an empty set if the set does not have any elements or it does not have any member. Empty set is also called a null set, and it is denoted by circle slash, or it can also be denoted by an empty brace. Okay? The set of all positive integers that are greater than their squares is the null set because there is no values of x where you square it. Okay, there is no values of x in the set of positive integers where it would be greater than their squares. That's why this set here is a null set. A subset is a set within a set. So the set A is a subset of B if and only if every element of A is also an element of B. We use the notation A subset of B. This is the notation for the subset to indicate that A is a subset of the set B. We see that A is a subset of B if and only if the quantification for all x such that x is an element of A if and only if x is an element of B is true. Therefore, A can only be a subset of B if all the elements of A are in the set B or is an element of set B. Rules to check if a set is a subset of another. To show that A is a subset of B, we need to show that if x belongs to A, then x also belongs to set B. To show that A is not a subset of B, we need to show that there is an element in A that is not an element of B. Rules to check if a set is a subset of another examples. Okay, to show that A is a subset of B, the set of rational numbers is a set of the real numbers because all elements of rational numbers is an element of the set of real numbers. Again, the set of all computer science majors in ADSU is a subset of all the students of ADSU or all students in ADSU. To show that A is not a subset of B example, we have here the set of integers with squares less than 100 is not a subset of the non-negative integers. There are also special theorems when we talk about subsets of a set. Here we have theorem number 1. For every set S, the null set is a subset of S, and the set itself is a subset of S. Theorem 1 basically shows that every non-empty set or null set, for every non-empty set, this not the null set. for every non-empty set S is guaranteed to have at least two subsets. So if your S is not an empty set, okay, it's a set with an element, you are already guaranteed to have at least two subsets. The first of that subset would be the empty set or the null set. This is where the null set is, and the set S itself. Okay, that is, the empty set is a subset of S, and S is a subset of C, represented by this theorem that we have here. Okay, a subset is called or said to be a proper subset if we wish to emphasize that the set A is a subset of set B, but the set A and B are not equal to each other. For A to be a proper subset of B, it must be the case that A is a subset of B, and there must exist an element of X of B that is not an element of A. And again, how do we show that two sets are equal? To show that two sets A and B are equal, we have to show that A is a subset of B and B is a subset of A. That is, A is equal to B if and only if for all elements of X is an element of A, if X is an element of B, and for all elements of X is an element of B if X is an element of A. The size of a set, let S be a set if there are exactly n distinct elements in S where n is a non-negative integer. We say that S is a finite set and that n is the cardinality of S. The cardinality of S is denoted by open bar S, close bar. Okay, this here means that this is the cardinality or the size of the set. Example here, let A be the set of odd positive integers less than 10. Then A in a roster method would be set of odd positive integers, so that's 1, 3, 5, 7, 9. And how many elements do we have here? We have 1, 3, 5, 7, 9. That's why we say that the cardinality of A, this is read as cardinality of A, or the size of A, is equal to 5. A set is called to be infinite set if it is not finite. Okay, it means to say that we could not list down the elements in that set because the elements in that set are infinite. Okay, the set of positive integers is infinite because there's infinitely many elements in this set, because the positive integers, the set of positive integers, can go on and on and on forever. You would never find the end digit or end value for the set of positive integers. That's why we say the set of positive integers is an infinite set. A power set, on the other hand, is basically just the set containing all the subsets of the set S as its element. Okay, given a set S, the power set of S is the set of all subsets of the set S. The power set of S is denoted by P of S. If a set has n elements, then its power set has 2 raised to n elements. Okay, what is the power set of the set 0, 1, 2? So for us to know how many elements do we have here, we have to identify how many elements do we have on the original set. We have 3 elements, right? We have 3 elements. So 2 raised to 3 would give us 8. So we are expected to have 8 elements in our power set, or basically 8 subsets. because again, the elements of a power set is the subset of our set. Now, what are the subsets of 0, 1, 2? Okay, set with an element of 0 is a subset. The set with an element of 1 is also a subset of this set. The set with an element 2 is a subset of this set. 0 and 1 is a subset. 1 and 2 is a subset. 0 and 2 is a subset. So this, we only have 6. What else can we have as subset? Remember the theorem number 1. We are already assured that for every non-empty set, you already assured 2 subsets, and that subsets are the set itself, 1, 2, 3, and the empty set. Okay, so these are the subsets of this set, and this basically are the elements of our power set of 1, 0, 1, 2. Okay, so this is the power set of this set here. And here is the solution of what we did. The power set P of 0, 1, 2, the set of 0, 1, 2, is the set of all the subsets of 0, 1, 2, which is the empty set, the set with the element 0, the set with the element 1, the set with the element 2, the set with the elements 0, 1, 0, 2, and 1, 2, and the set itself is a subset of itself. And that is all for the introduction of set theory.